The second possibility that can appear when we apply the Heaviside method for partial fraction decomposition is the one in which there are repeated factors, which means that some roots of the denominator of f of s are repeated, some poles of that function are multiple. In this case, we've assumed that the roots of this denominator contain one repeated factor. There is only one repeated pole, one multiple pole, which is minus p1, and its multiplicity is k. So the pole appears k times. Well, this doesn't mean that we lost generality. If there were more than one multiple pole, all the calculations we're going to do from now on would be done the same. But in order to keep things clean, because as you'll see calculations get a little messy, we've assumed that there's only one pole. So first thing we have to do is to replace this way of writing the function by a factorized way. And as you can see, the s plus p1 to the k term gives rise to k factors, each one with a different exponent in the binomial of the denominator. The first one is the first denominator is s plus p1 to the k, and its associated residue is r1k. This k here matches the k in the denominator, in the exponent. The second term is s plus p1 to the k minus 1, and therefore the associated residue is r1 k minus 1. So we have to continue with this pattern until we reach r12 divided by s plus p1 to the squared, and the final factor r11 over s plus p1. And then the simple roots come, each one with their associated residue. Here we have r2 over s plus p2. So first of all, we have to multiply both sides of the equation by s plus p1 to the k. 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 All of the other terms the same. And s plus p1 to the k. And let me rewrite this equation. In the left hand side we have the same, f of s times s plus p1 to the k, and here we have s plus p1 to the k cancels out with this, so only the residue is left, plus r1 k minus 1 times the binomial s plus p1, and here is k minus k plus 1, so the exponent is 1, plus r1 k minus 2 times s plus p1 squared. The same thing with all the other terms, so r1 2 times s plus p1 to the k minus 2 plus r1 1 times s plus p1 to the k minus 1. And in the case of the other poles, there's no simplification. S plus p1 to the k. So now we can assume that s is equal to minus p, but first let me save a copy of this that will come in handy later on. Okay, now if we assume that s is equal to minus p1, here this is 0, this is 0, this is 0, this is 0, and all the rest of terms are 0, leaving only r1k in the right hand side. So this is the formula for the first residue. What do we do for the rest of the residues? Well, the operation that we have to apply is differentiation. I need some space here. Okay. Let's differentiate both sides with respect to s. So, as I need some time, let me do a trick here. There we go. The derivative of a constant is 0. The derivative of this term is r1k minus 1. The derivative of this term is 2 times r1k minus 2 times s plus p1. The exponent decreases in 1 unit, plus the derivative of this term here is k minus 2 times r12 times s plus p1 to the k minus 3, plus again k minus 1 times r11 times s plus p1 to the k minus 2. And in the rest of the terms we could calculate the derivatives, but we don't really care because we know that when we apply s is equal to minus p1, all of them will go to 0. And that's exactly what we're going to do now. We're going to assume that s is equal to minus p1, and what we get here is the derivative with respect to s of f of s times s plus p1 to the k in s equal to minus p1 is equal to 0 plus r1 k minus 1 plus 2 r1 k minus 2 times this is 0. All the rest of terms are 0 because there's still some s plus p1 term multiplying the residue. So here we have the formula for the second residue. The next step is obviously taking a new derivative of the function. So here we would have the second derivative with respect to s twice of f of s times s plus p1 to the k. This is equal to, let's look at this expression, at this part of the previous equality. The derivative of 0 is 0, the derivative of a constant is 0, the derivative of this is 2 times r1 k minus 2 plus all the terms, the derivative of this here is k minus 2 times k minus 3 times r12 times s plus p1 to the k minus 4, and the derivative of this part is k minus 1 times r11 s plus p1 to the k minus 2, and all the rest of terms whose derivative we don't care about. And again, making s equal to minus p1, this goes away, and we only leave here 2 times r1 k minus 2. So here is the expression that leads to that particular residue. Well, you can see the mechanics of the method. So now we can apply it to an example. Let's calculate the inverse Laplace transform of the function s plus 2 over s times s plus 1 cube. So first of all, the expansion. This is equal to s plus 1 cube, and its associated residue is 1, 3, plus s plus 1 squared in the denominator and r12 in the numerator, r12. The third factor with r11, and the residue associated to s is r2 over s. Multiplication by s plus 1 cube, 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 and s plus 1 cube. And we can write everything after cancelling out things in the expression. So we have s plus 2 over s is equal to r13 plus r12 times s plus 1 plus r11 times s plus 1 squared plus r2 over s times s plus 1 cube. So before making s equal to minus 1, let's save a copy of this, and now we can assume here that s is equal to minus 1, and therefore here we have 0, 0, 0, and r13 is equal to minus 1 plus 2 over minus 1, that is minus 1. Okay, the second residue comes from the differentiation, so let me apply the same trick. Great, the derivative of this part here is the derivative of the numerator, which is 1, times the derivative times the denominator, minus the derivative of the denominator, which is 1, times s plus 2, which is the numerator, over the denominator squared. This is s minus s plus 2 is minus 2 over s squared, and this is equal to the derivative of a constant is 0 plus r12 plus r11 times s plus 1 plus something we don't care about because we know it will eventually be 0. We save a copy of this, and then we apply the condition s is equal to -1, and therefore we have -2 over -1 squared is 1 is equal to r12 plus this is 0, so r12 is equal to -2. So as you can see, it's a lot easier with numbers. A further differentiation leads us to what if we have here -2s to the -2. Its differentiation gives us 4s to the -3 is equal to 0 plus r11, and if s is equal to -1, then the previous expression gives us -4 is equal, sorry, there's something I've missed. Yes, here it is. The derivative of this part with respect to s is 2r11 times s plus 1. So don't forget that too. That's a common mistake. Well, maybe not that common. 0 plus 0 plus 2r11. So it's 2r11, and therefore r11 is equal to -2. We have all the residues related to the pole in -1. We only have to calculate the residue associated to the pole in 0. Let's do it very quickly. The original function was s plus 2 over s times s plus 1 cube. We multiply that by s and assume that s is equal to 0. That is r2, and this is 2. Well, this cancels out with this. This is 2 over 1. Therefore r2 is equal to 2. So let's take all our residues and take them to the original expansion. r13 is equal to -1. So here we have -1. Let's see what r12 is. r12 is equal to -2. So here we have -2. r11 is -2 again, and r2 is 2. And as a consequence, the inverse Laplace transform of f of s is -1 times t squared over 2 times e to the minus t, minus 2 times t e to the minus t, minus 2 times e to the minus t plus 2. And that is the result of the problem we wanted to solve.